Hello friends of electrical motors. In this video I will show you the 4 types of losses in electrical motors. I also show you in which motor components the losses occur and what they are depend on. Additionally, I will tell you what you can do to reduce the different motor losses. So let's get started. As you can see here in the diagram, the losses of electrical motors can be divided into ohmic losses, iron losses, stray losses and mechanical losses. Ohmic losses are also often called copper losses, and iron losses are also called core losses. Now I will go into the further classification of losses and what they depend on. Before I forget, subscribe to the channel now to get more detailed information about electrical motors. Ohmic losses occur primarily in the windings of the stator and are dependent on the resistance and the current. The ohmic losses can be divided into frequency-dependent and frequency-independent losses. The frequency-independent losses depend on the dimension, so the length, the cross-sectional area of the wire and the material, for example copper. A strong increase of the motor temperature also increases the resistance and therefore also the losses. You should always ensure that the electrical motor is well cooled. Otherwise, the temperature of the windings will quickly increase. The frequency-dependent ohmic losses rise with an increase of the frequency due to the skin effect. The skin effect reduces the area through which the current can flow. To reduce the effect, wires with a large diameter are divided into several separated wires. However, dividing in too many wires also increases the resistance due to the proximity effect. So it is not easy to find the best number of parallel wires. If you have more specific questions, just write them in the comments. I will answer your questions and help you out. Induction motors also have high ohmic losses in the rotor, so that the rotor quickly gets hot. It is very difficult to dissipate the heat from the rotor. That is why Tesla uses liquid cooling of the shaft for the induction motors. Iron losses can be divided into hysteresis losses, eddy current losses and additional losses. As you can see from the equation, the losses per weight depend on the frequency and the maximum flux density. This means that the faster the rotor rotates, the higher the iron losses will be. And the smaller the electric motor is designed, the less space is left for the magnetic flux, and therefore the flux density gets higher. The proportional constant C depends on the material and how it is preceded. Magnetic materials are divided into many small domains, which all have a different magnetic orientation. Losses occur when the magnetic orientation of the domains are changed. These magnetization losses are called hysteresis losses because the material passes through a hysteresis during the magnetization. The losses depend on the area of the hysteresis of the material which is passed through during the remagnetization. In order to keep the losses low, soft magnetic materials such as electrical sheet with a small hysteresis curve are used. Eddy currents occur when the magnetic flux in the stator is changed. The eddy currents generate losses in the stator and heat the stator up. To reduce losses, the stator is divided into separated sheets, insulated from each other. This reduces the eddy current losses significantly. As I just said, magnetic materials consist of domains which are separated from each other by walls. A change of the magnetic field can cause a shift of the walls which results in losses. These losses are called additional losses or excess losses. I'm making another video especially about electrical sheets for electrical motors. To ensure that you do not miss it, subscribe to the channel and activate the bell. Iron losses occur primarily in the stator and the rotor, but eddy current losses can also occur in permanent magnets. The losses in the permanent magnets are usually low, but critical because magnets usually do not have a good temperature resistance. Mechanical losses can be divided into friction losses and ventilation losses. Friction losses depend on the speed and occur, for example, in the bearings. To keep friction losses as low as possible, the bearings should always be properly lubricated. The bearings must therefore not become too hot, otherwise the lubricant will dissipate. Friction losses also occur in the brushes of separately excited synchronous motors and commutators of DC motors. Ventilation losses occur in electrical motors with non-round rotors and also depend on the speed. For example, SR motors or separately exceeded synchronous motors have rotors that are not absolutely round. The ventilation can be reduced by casting the stator and bending the rotor. If the right material is used for the casting, the heat dissipation can also be improved. However, the ventilation in electrical motors can also be used to transport the heat out of the center of the electrical motor. This distributes the heat better in the electric motor and reduces hotspots. Stray losses are the stray of construction elements and materials, but also the stray losses that occur in the production process and very small deviation from the design. The stray losses are therefore difficult to estimate and can be approximately 1% for electrical motors at peak load. The visualization of the conservation of the power of electrical motors and generators is illustrated with the help of the power flow diagram. In electrical motors, the diagram shows how much electrical input power is supplied and how much mechanical output power remains after the power losses have been dissipated. In a generator, the flow of the power dissipation reserves. This means if you have too much friction in the bearings, there's less power left to convert it into electrical power. The losses of AC motors are of course also strongly depend on the control strategy and the modulation methods of the used inverter. These directly influence the frequency of the current and therefore the ohmic losses, but also the iron losses. If you enjoyed the video, you must do me a favor. Share the video with your network. Like the video and consider to subscribe to my YouTube channel. Thank you for watching and I wish you all an excellent efficiency.